Next to my revision videos. We'll kick off with energy. So first of all, kinetic energy, which is a half mv squared, half the mass times the velocity squared. We can put that in a triangle. If we keep the half m as an object, we keep the v squared as a number and the kinetic energy. And we can see that if we want v on its own, we end up with root ke over half m. And I'll leave you to figure out the equals. Next we have the GPE. This is things off the ground, and the higher they go and the heavier they are, the more gravitational energy they have. So we end up with mgh. And in most tests they'll give you what g is, and usually it's regarded as 10. Again, we can whack that in a triangle. I'm running out of space for my triangles, and this time we'll have three terms, m, g, h for our GPE. And again, cover up the one you want, write what you see, and that's an easy way of rearranging. And the last one is electrical energy, and that one almost spells out a word, VIT. The voltage times the current times the time it flows for, that will give you the total energy flowing. Next, for this bit, I'd like you to pause the video for each bit where you think you're wondering what's going to go in. See if you can guess ahead of time. So pause it now. And you probably haven't paused it, so I'm just going to go ahead and do it. So, conservation of energy underpins the whole running of our universe. And it boils down to the fact that you can't make or destroy energy. There is exactly to the joule the same amount of energy as there was the day it was made. All you can do is change it, transfer it, just put trans, or convert it, no, store it. It's early in the morning. So we can take something like a simple light bulb, and we can show that electrical energy goes in, is converted to heat and light, and conservation of energy will tell us that every joule that goes into this system is accounted for. There is no such thing as truly lost energy. It just goes into a form that we can't do anything with. So, a good example of this is a pendulum. We load it up at the beginning here with GPE, and at this point we'll say it's the maximum. So we might take the height this thing is at, might find the mass of this thing, calculate its GPE, and at the very second that you're about to let go, we say its kinetic energy is 0. In an ideal world, all of that gravitational potential energy will be converted into kinetic energy, and so whatever value we had for our GPE up here will appear down on our KE here. And again, we're assuming that in our system that's as low as we're going to get. So, for all intents and purposes, we can put 0. And in a perfect world, we'd get an exact same height for our pendulum on the other side. And again, we'd have maximum and we'd have 0 at the second it stopped. However, in real life, that's not true. The world is far more complicated than that, and there is always going to be energy losses. So this pendulum on this side, and if you remember we did the experiment where we stood at quite a delicate point for being hit, it comes lower, and that's because of energy losses. It's mostly lost as heat at this point here, and with air resistance acting as the ball tries to cut through the air around it. So that's a pendulum example. Next, work done and power. This was the one where we did step-ups. And we found the work done to do one step up, and we also lifted bags and put them on the top. We looked at the rowing machine, and we looked at swimming and I believe cycling. So it all boils down very simply to the work done equation, which is force times distance. We've done that once before in the previous test, but it's such a key equation we're doing it twice. And then the other one is power, and that's the amount of energy used per time. So the unit can be given as joules per second. However, it can also be expressed as watts, named after James Watt, who figured it out. And another form of the equation could be this energy here. Well, if it's the case of we are doing some work, then they're the same thing. So we have work done over time. Work done is just energy. The unit is joule. So you will see them used interchangeably, and it really doesn't matter. Takes us on to skid marks. Now, we've learned the equation for the car moving, kinetic energy, a half mv squared. And we know that if this car is to stop when it puts its brakes on, it must apply a force backwards from the brakes. So what we need is a total work done to be equal to the kinetic energy in the car. The work done will be acting this way to retard the motion of the kinetic energy moving that way. Well, we can write this out as force times distance. So we've got our two equations. And then to find out how far we're going to skid, we just need to rearrange this equation. And what we'll get is D is equal to half mv squared divided by the force acting from the brakes. And what you'll discover there, if you plug the numbers into the velocity, is that if you start with a velocity of 2, for example, and compare it to the velocity if it was 4, by doubling the velocities, try and find out, and it'd be quite handy to know for Tuesday, what happens to the total distance travelled in both cases. What is the relationship between them? What is this multiplication factor? Next, momentum and force. Moving objects with a mass and a velocity have momentum. So the equation is very simple, m times v. The unit for this is a bit of a made-up one. If mass is measured in kilograms, velocity is measured in meters per second, then very unimaginatively, momentum is kilograms meters per second. We can then turn that into a force. Here we have, if you remember the Bruce Lee lesson, we talked about the idea of generating a force over a small area and showed you videos of the 1-inch punch. So if we assume his fist has a mass and it's moving with a velocity, now the key to this is time. If the time for you to go from moving to not moving is very, very small, you will generate a very big force. And so the equation ends up looking like this. Change in momentum divided by the time of that change. And as you can see, if that number is very small, then this number is going to be very big. And that's the key behind generating a lot of force. In practical terms, they use this in car safety by reducing the time to decelerate, decelerate, I've got that backwards. The beauty of rewind. By increasing the time to decelerate, you reduce the force acting on the car. And in practical terms, in your car, it will be such things as airbags, seat belts, and crumple zones, all designed to slow you down over a longer period and hence reduce the force acting on you. And that concludes my video. It's not everything, so go through your book, look at the list on Edmodo, and good luck on Tuesday.